got a fraction up there, and it's two fractions adding, so I'm going to need a common denominator for those two. And if you look at this one here, that's also a fraction that's being added or subtracted, so we're going to need a common denominator there. And I have two fractions up here that are being added, and they're going to need a common denominator. And that has nothing to do with the fact that this one has an x and this one has two x's. The idea for common denominator holds for every single type of fraction. So just a little preamble about what common denominator is and why you have to do it. This expression says 2 divided by 3 plus 4 divided by 5. And according to your order of operations, you're supposed to do division before you get to addition. So in this expression, you would have to do 2 divided by 3. Then you would have to do 4 divided by 5. And then you would be allowed to add them together, but only after you've done those divisions. Now that's going to be a mess, because 2 divided by 3 is 0.666666, and it never stops. 4 to 5 ends up being 0.8. That's not so bad, but if you add 0.8 to 0.666666, you end up with a decimal that goes on forever, which means you'll have a rounding error as soon as you write that down. So I'd like a way to try and weasel around order of operations so that I can do the addition first before I do the division. And the trick is, if I'm dividing both of these things by the same number, then I can just save that to the end, but only if they're being divided by the same number. So I'm going to think about that. Currently, they are not being divided by the same number. This one's being divided by 3, and this one's being divided by 5. But a neat little feature of fractions is that that line is a division. So if I throw a multiply by 5 up here and a multiply by 5 down here, those two things would divide each other out, right? Times 5 divided by 5. And I know it looks like it says multiply by 5 here, but any number in the basement of a fraction, even if it says multiply here, that's a division. Anything down here is division. Why would I do that, you might ask? Well, 2 times 5 is 10. 3 times 5 is 15. If you do 10 divided by 15, you get 0.66666. It's the exact same value as this fraction. It's just a different form. And why did I pick 5 here? Well, this had a 3. It didn't have a 5, so I introduced a 5 into top and bottom and got a form that has a factor of 5 in it. If I do that to this one, 4/5, this fraction is missing the division by 3, so I'm going to introduce it. I end up with 12 divided by 15. Now, because these are divided by the same number, it doesn't matter if you do 10 divided by 15 plus 12 divided by 15, or if you just take the whole total. 10 and 12 is 22 out of 15. The answer to that will be, what was it? 1.466666, whatever, and it would be the same as if you did these as decimals, but it doesn't have the rounding error in it. So you've been doing common denominator for a good long while now. I think probably 6 years at this point. I don't know if anyone ever pointed out to you that it was just a workaround around order of operations, but there it is. when I get to this fraction here, I'm not going to be able to write this in decimal form. I don't even know what x is. So this is where having that common denominator skill actually comes in handy, because I can't shortcut with decimals the way I could shortcut with this one. I have to use the common denominator technique. Fortunately, it doesn't change with an x. I see a fraction here that does have a 4 in the bottom, and I have a fraction here that does have a 7 in the bottom. To make these denominators match, I just need to introduce a factor of 7 to the front fraction and a factor of 4 to the back fraction. That ends up giving me 7 times x is 7x over 28, and 3 times 4 is 12. 7 times 4 is 28. So 7x's divided by 28, subtract 12 divided by 28 are both divided by 28. So 7x subtract 12 divided by 28. And I've managed to write that as a single fraction. Okay, up here, same thing. I can't write this as a decimal because it has an unknown in it. And I can't write this as a decimal because it has an unknown in it. So I'm going to have to combine these using common denominator. So I've got a fraction here, and I have a fraction here. This one has a factor of 5, but needs a factor of 3, so I will introduce it. This one has a factor of 3, but needs a factor of 5, so I will introduce it. That gives me 3x over 15 here, and 10x over 15 here. Now when I combine those, 3x's plus 10x's, well, those are like terms. They both have an x attached to them, so I can combine them. 3x's and 10x's is 13x's out of 15. So it didn't matter if there were no x's, an x in just one fraction or an x in both fractions. The basic common denominator process works for all of them, and you're able to reduce it down to a single fraction, or a single fraction with some complicated stuff in the top because you couldn't combine the like terms. And to clear this off, we'll try some more complicated examples. Well, these ones are still fractions plus a fraction. It's a little different from the last set, is now the x's are showing up in the denominator, not just the numerator. But again, it doesn't change the operation. I see a fraction plus a fraction, and they have different factors in their denominators. So I need to take what was there and then see what factors each fraction needs. This one has an x, it needs a 5, so I introduce a 5. This one has a 5, it needs an x, so I introduce an x. That gives me 2 times 5 is 10 over 5x. 3 times x is 3x over 5x. And these are both divided by 5x, so I can combine them as 10 plus 3x over 5x. I've written these two things as a single fraction. This one, I see a fraction with an x squared in the denominator, and I see a fraction with a 4 in the denominator. This one has the x squared, it needs the 4, so I introduce the 4. This one has the 4, it needs the x squared, so I introduce the x squared. That gives me 3 times 4 is 12 over 4x squared. And x times x squared is x cubed over 4x squared. Those are both divided by 4x squared, so I can combine them as a single fraction, like so. 12 and x cubed are not similar terms, because this one doesn't have an x at all, this one is only x, so I'm complete there. For this one, same thing. I have a fraction with a 5 on top and a 2x squared in the bottom. I have a fraction with a 3 on top and a 7x in the bottom. And we're going to try and be efficient here. This fraction has a 2, it has an x, it needs a 7, and put it in both top and bottom. This fraction over here has a 7 and 1x, which means it needs another x to get up to x squared, and it needs the 2. So I'm going to have to introduce that in both top and bottom. 5 times 7 is 35. 2 times 7 is 14. 3 times 2 is 6. 7 times 2 is 14. And x times x is x squared, which gives me my common denominator. And I can combine those now. 35 plus 6x is 14 over x squared. These aren't like terms, so I'm done. I've combined these two things as a single fraction. Now, like in this line, you could have seen that this one had an x squared but didn't have an x, so you add an extra x in there to make x cubed. You could have done that, but it's going to balloon up your expression. So you try to add or introduce just the minimum amount of bits so that you get a match. I'm going to clear these off. We'll try a couple more complicated examples. So again, I have two fractions. The denominators don't match, so I need to introduce the pieces I need. These are different because instead of being a number or an x all multiplied together, this has an x plus a number. So that ends up being like a factor on its own. So I have a fraction like this, and I have a fraction like this. This fraction has, sorry, that should be a 5, has the x plus 5. It needs the 4, so I'm going to introduce that. This fraction has the 4. It needs the x plus 5, so I'm going to introduce that. Will give me 2 times 4 is 8. 4x plus 5. Subtract. 3 times x would be 3x. 3 times 5 would be 15. For 4x plus 5. I can write that all as a single fraction. It'd be 8. Subtract all of this. So an 8 subtract a 15 would be -7. And the negative 3x is a negative 3x all over 4 the x plus 5. So you'll notice that at one place here, I did expand into the bracket, and there was another place here where I chose not to. Now the reason for that is by expanding into this bracket, I was able to see that I had two like terms here, a number with no x and another number with no x that I could combine into -7. In the bottom, I don't have any adding or subtracting to do. So I don't have any like terms to gather. So it's going to be easier for me to see what bits are in that denominator if I leave it like that. So in general, and as soon as you use the word always in math, it ends up being false. But in general, expanding the numerator helps you down the line. Not expanding the denominator helps you along the line. So if you can try and keep that in your head as you're simplifying these, it'll help you out. Okay, so next one. I have a fraction like this. I have a fraction like this. This fraction has the x minus 3. It needs the x plus 6. This fraction has the x plus 6. It needs the x plus 3. So if I multiply this out, a 5 and an x is 5x. A 5 and a 6 is 30. 2 and an x is 2x. 2 and a 3 is 6. And both of these are over x minus 3, x plus 6. X minus 3. Oh, that should be a subtract then. That makes that a subtract. Apologies. This one is x plus 6 over x minus 3. And those two fractions are added together. So if I combine them as 1f or 5x plus 30 plus 2x minus 6 over x minus 3, x minus 6. Gathering the like terms, 5x's and 2x's are 7x's. 30 and negative 6 is plus 24 over x minus 3, x plus 6. So again, I did the FOIL on top because it allowed me to gather like terms. I did not do the FOIL in the bottom so that I could see what factors I still had kicking around. The third one here, see my careful screen planning has been falling apart. This fraction here has 2 powers of x minus 3 in its denominator. This only has a single power of x minus 3. If you just did this like a robot, you might find yourself introducing a third x minus 3 over here and 2 x minus 3's over here, which is going to put squares in your numerator. I don't want to do that. This thing is x minus 3 multiplied by itself. This one already had an x minus 3. To make these things have common denominators, I only need to introduce one factor over there. And now I have a match. So when you've got this stuff going on, if you can match factors and realize that 2 factors here and 1 factor here only needs this one bumped up by 1, it will save you a lot of mess in your algebra. So this combined would be 7x, and 4 times x is 4x. 4 times negative 3 is negative 12. All of that is going to be over this fraction. Seven x's and 4x's are 11x's. Subtract 12, and I'm just going to write this as x subtract 3 squared. So even though this is getting messier as we do more complicated examples, the basic idea that you just need to introduce powers to the denominators of each fraction so that they have a match has stayed the same. You haven't had to do any new math. It just looks funnier because you're putting more complicated things in to the old idea of common denominator. I'm going to clean this off. We've got 2 more examples, and then I think we're good to go. Okay, there we go. you might be tempted to take this fraction, it's 8x plus 15, and you might be tempted to introduce this on both the top and the bottom. And then you'd have to do it for the second fraction as well. So you'd end up with x minus 4, introducing this into the top and the bottom. Good Lord. X squared plus 5x minus 6 was already there, and x squared plus 8x plus 15 has been introduced. Yuck. To finish this, I'm going to have to throw 3 into there, so it's a 3-way FOIL. And then up here, I'm going to have to multiply x by all of these things, and then negative 4 by all of these things. It's going to be a giant mess. And I mean, that's because we just sort of mindlessly took whatever was in this denominator and introduced it to the front, and took whatever was in this denominator and put it into the back. But you might have overdone it there. Because these things are trinomials, and trinomials factor sometimes. So I'm going to do that. I just did catch here, I wanted this to be a positive 6. So I'm just going to fix that before we get too carried away. To factor this thing, I need an x in each bracket, and then I need a pair of numbers that add to 8 and also multiply to 15. So the things that multiply to 15 are 1 times 15, negative 1 times negative 15, 3 times 5, and negative 3 times negative 5. These would add to 16, so they're no good. These add to 8. That's the pair I want. So x plus 3 and x plus 5. Get that out of the way. I'm going to try and do the same thing to the second one. Two brackets. I need an x in each. And I need a pair of numbers that add to 5 and multiply to 6. So things that multiply to 6 would be 1 and 6, 2 and 3, negative 1 and negative 6, negative 2 and negative 3. These two things add to 7, so they're no good. These two things add to 5, that's the pair I want. Out of the way. Now if you take a look at those factors over there, I don't have to introduce the entire trinomial, because once I factor it, I can see that this thing, both of them have a factor of x plus 3 in that denominator. So I don't need to add it again. The only thing missing from this bracket, or this denominator, is a factor of x plus 2. This has one, this one didn't. And the only thing missing from this denominator is the factor of x plus 5. This FOIL is a lot simpler than that one, and this FOIL is a lot simpler than that one. So by being a little tactical and taking a look at what's in your denominator first before you try to do this common denominator thing will save you some extra work. So if I try and clean this expression up, I'm going to end up with 3x plus 6, 3 x's and 3 2's. Subtract x and an x is an x squared, x and a 5 is a 5x, negative 4 and an x is negative 4x, and negative 4 and 5 is negative 20. all over x plus 2, x plus 3, x plus 5. I keep going to clean this up. I've got 3x plus 6, subtract x squared, subtract 5x, subtract negative 4x, which is this, subtract negative 20, that. Now I just have to gather my like terms. I have a negative x squared, it's the only x squared up there. I have 3x's here, minus 5x's plus 4x's. So 3 minus 5 is negative 2, negative 2 plus 4 is positive 2x's. And I have a 6 and a 20, that gives me 26 over x plus 2, x plus 3, x plus 5. So by checking to see if these things factored, you were able to spot that you only needed to add one more linear term to the denominator rather than having to throw in another quadratic term to both denominators. As with the other examples, don't FOIL the bottom, leave it so you can see what the factors are. But do FOIL the numerator, because that will allow you to gather like terms. And we'll get to this spot right here. I have a quadratic on top. It is possible that that factors 2. So let's sort of spend a minute thinking about that. That's negative x squared minus 2x minus 26, because you always have to pull out the a factor. I would need two numbers that multiply to 26 and add to 2. So negative 26 would come from negative 1 times 26, negative 2 times 13. And that's it. Well, I guess there's 1 times negative 26 and 2 times negative 13. That adds to 25, which is not negative 2. That adds to 11, which is not negative 2. That adds to negative 11. That's negative 25. None of these combos work. So this thing doesn't factor. So I've got this set up there. I know that doesn't factor. I know what's in the denominator. That is as reduced as it can go. Okay, I'm going to erase this. We're going to try one more monster example like this one, and then it'll be off to the practice problems. Got another set of fractions here with trinomial in the denominator, which is highly suspicious. So before I try and common denominator them, I'm going to see if these factor. Who knows, maybe they don't. So I need two brackets. I need an x and an x. Now I'm going to need two numbers that multiply to negative 24 and add to 2. So negative 24 could be negative 1 times 24, negative 2 times 12, negative 3 times 8, negative 4 times 6. 5 doesn't go, 6 goes. I've already got 6, so it's the full list. That would be 25, that would be 10, that would be 5. This would give me positive 2. So I'm going to try the other combo. There we go. 4 times negative 6 is negative 24, and 4 subtract 6 is negative 2. So x plus 4, x minus 6 are the combination that I need. And we'll try this other one here. On the great mystery, will it factor? So I need an x in both brackets, and I need two numbers that multiply to 32 and add to 12. So 32 is 1 times 32, 2 times 16, 3 doesn't work, 4 times 8, 5 doesn't work, 6 doesn't work, 7, 8 works, but I've already got it. So there's my full list. That's 33. That's 18. 4 and 8 is 12. That's the combo I want, because that's 12. So looking at those two fractions there, I look at what's in the denominator and I see which factors are in common. That's an x plus 4 and an x plus 4. Surprise, if you didn't see that coming. So this fraction here has the x plus 4, it has the negative 6, it needs the x plus 8, so in it goes. This fraction has the 4, it has the 8, it needs the x minus 6. Well, there's a lot of FOIL in this one, but I believe in you. You can do it. Maybe I believe in me because I seem to be the one doing it, but hey, we can share the wealth here. X and x is x squared. X and 8 is 8x. 2 and x is 2x. 2 times 8 is 16. Plus x and x is x squared. X and negative 6. Negative 3 and x. Negative 3 and negative 6 would be positive 18. All over top of x plus 8, x plus 4, x minus 6. All right, so just gathering like terms and then we're done. X squared here and x squared here gives me 2x squareds. There's an 8x here, 2x, negative 6x, negative 3x. So 8 and 2 is 10. 10 minus 6 is 4. 4 minus 3 is 1. I have a 16 and an 18, so those together are 34. All over x plus 8, x plus 4, x minus 6. All right, so I'm just going to check because there is a possibility that this thing up here factors. So if you pull out the a value, it's 2 times x squared is 2x squared, 2 times 0.5 is 1x, and 2 times 17 is 34. I would need to find two numbers that multiply to 17 and add to 0.5. I know 17 is prime, so it's 1 times 17 or negative 1 times negative 17. Neither of these add to 0.5, so that's not factorable, which means that expression is simplified as far as it can go. So again, if you see trinomials in the bottom, which is very suspicious, try factoring them. See if you can just introduce a single factor instead of having to introduce the entire trinomial when doing common denominator. FOIL the top, leave the bottom, so you can gather the like terms. Check if this is factorable. It probably won't be, and then you're done.